Okay, so the next speak is by Shivaram, and it's an improved lower bound on the length of locally improving policy sequences in MDPs with large action set. Okay.
That's right. Yeah, so don't lose your appetite for MDPs and some more theory, because that's what I'm going to serve you. Dibyangshu is a current student, but Pratyush and Wajid, these were undergrads who graduated some years back. This is a lower bound, okay, rather than an upper bound. So I'll begin by telling you what the problem is that we take up and solve over here, and then spell out our own contribution, right, what we have done over and above existing work. It's a lower bound, so I'll share with you very briefly sketches of two constructions, and then finish with an open problem. Okay, we did our best, but we didn't quite solve it. There's a little bit distance to cover, so I'll tell you at the end what that is. And begin at the beginning, okay? So I think for the third time now in 3 talks, what is an MDP? Well, I'll keep it brief. Okay, so here's a picture of an MDP. This one has 3 states, 2 actions. So at each of these states, you can take either the 0 action, which is black, or the 1 action, which is dashed and red. You have stochastic transitions. You have a reward associated with each transition. This particular MDP also uses a discount factor to discount an infinite stream of rewards. All right, so you can start at any state and can follow a policy. By now you know what that is. A policy essentially is an assignment of one of these actions to each of the states. Okay, so if you do it, okay, you can enumerate all 8 of the policies which are available. There are 3 states and 2 actions. And for example, if you started at state 1 and started following policy 001, right, which means 0 at the first 2 states and 1 at the third state, the expected long-term reward you'll get is 5.07. Okay, that's the meaning of this. And you can calculate these numbers by solving something called Bellman's equations. Now, it is well known that you take any 2 policies, their value functions need not be comparable. Okay, here's an example of that. You have these 2 policies, 100 and 111. You notice that from the first state, 100 gives you a lower reward than 111. If you go to the third state, right, the value is higher. Okay, this could happen in general, but it will not happen if you're comparing policies which are neighbors, in the sense that they differ only in one action. Okay, they do the same thing in all but one state, and on that one state they're doing different things. You take any pair like that, right, you'll notice that one value function dominates on every column, the other, up to equality. Okay, you can have equality in some cases. So that being the case, you can draw a graph in which each of the policies is a vertex, its neighbor is connected by an edge, and the orientation of that edge is in the direction of domination. Okay, so here we saw that 100 is dominated by the other way around. 101 is dominated by 100, so 1001 will go to 100. Okay, in this similar manner, you fill up all the other entries. There's nothing sacred about having 2 actions. You can have MDPs with more actions. This is a picture of an MDP with 2 states, 3 actions. Pretty much the same story. Now you have 9 policies. You have a more complicated looking graph with 9 vertices, lots of edges. But again, the concept of neighborhood, right, and these directions is well defined. It stays the same. Now, these graphs, okay, which are discrete, are called induced LP digraphs. Okay, they have connection with the linear program that the MDP induces. Each of the policies here has an association with the vertices of the polytope of the linear program, but that's all for later. It's just called an LP digraph for now. What kind of properties do these have? First, you'll notice that these digraphs are, okay, never mind, let it be there. Acyclic, okay, you won't have cycles. So you start anywhere, you start following the outgoing edges, you'll never come back to the same policy. They have a unique sink, okay? So doesn't matter where you start, right? You keep following the edges, you'll end up in one vertex in any of these graphs, one on the left, one on the right. Okay, so that unique sink is also called the optimal policy for the MDP. Of interest to us here is what is called a locally improving policy sequence. Okay, so what is that? So I've given you a couple of examples here. So starting from, let's say, 101, this is a sequence of policies. It's a very short one, okay, that goes from this policy all the way to the sink. Here is a longer one, okay, that goes through 5 or 6 policies before it goes to the sink. So this is essentially a path, okay, through these policies that will go to the sink. It's the kind of thing that simplex, for example, will follow, right, when it is being executed. Similar examples over here. I think in the literature on LP and so on, they call this sometimes C monotone paths. These are paths on which the objective function of the linear program will monotonically increase. Yeah? Transitive means A implies B, B implies C. Yes, it is. Yeah, it is. Yeah. Okay, so what is an LIPS? It is some directed path leading from some vertex to the sink. Okay, and clearly you can see there's an exponential number of these. Of interest to us, okay, is the maximum length of an LIPS in an LP digraph. Okay, so that is, in fact, it's got a name. Okay, it's called the C height of the LP digraph. I think for this one I calculated before coming here, that is 5. Okay, 5 edges. If you count it in terms of number of vertices, it is 6. I've not really done the counting over here. That's the longest LIPS on this particular LP digraph. Okay, so broadly the question we ask in this work is how long can the C height be? Okay, to make it a little bit more precise, the question we ask is this: define f of nk to be the largest C height of an LP digraph induced by some n state k action MDP, which means you take all possible n state k action MDPs. Each of them is going to induce an LP digraph. Each of those is going to have a C height. Take the max over all of that as a function of n and k, right? Call it f of nk. What we would like to furnish is a lower bound on f of nk. Okay, not an upper bound, lower bound. So what does it mean? It means we want to fill in this blank. Okay, we want to say f of nk is greater than or equal to some number, and we want to make that number as large as possible. Okay, so while doing this, keep in the back of your mind that the largest we can hope to fill in here is k to the n. Okay, so the number of policies, deterministic policies in such an MDP is, you have k things you can do at every state, right? So it is k to the n. You can't expect to have a number larger than that, but yeah, presumably you can have something that is smaller. Okay, so this is the problem that we intend to solve. You might ask, is it, worth solving this problem? It's not going to, help us in our fight against global warming, but it is, something arising from scientific curiosity. I've been working with MDPs for many years now, and so I feel like something as basic as this about MDPs, the structural property of them, is still not known to us, right? So it is curiosity that's killing the cat. I'm going to come to that. Yeah. Okay, so what is it that we inherit and what is it that we do? All right. So this question is answered affirmatively for the special case of MDPs that have two actions. Okay, this is 30, 40 years back. In this 94 paper, it is shown that this is an MDP. In fact, it's an instance of their construction with n equal to 4. Okay, you can take a black action or a red action. These are not really decision-making states. It's just there for convenience. But this particular MDP, there is a sequence of 2 to the n policies that you could possibly go through. In follow-up work, okay, this Ashutosh et al. Is me and my students 5-6 years back. We tried to extend this to general k actions. Okay, not 2 actions, but maybe 5, 6, 7 k actions. We had a construction maybe slightly inspired by this, where every state has like a sibling. Right, we managed to do something with multiple actions, and the best we were able to come up with as a lower bound was square root of k to the n. Okay, this is really read as k to the n over 2, with the n over 2 happening because each of these states has a sibling, right? So you kind of halve the exponent by doing this. So what I'm going to describe next is this ICAPS paper, which improves upon this square root of k to the n bound. Okay. Here are our results. For the special case of having only 2 states, okay, that's a very simple problem, but with k actions, we show that indeed f of 2k is k square. Okay, there is a Hamiltonian path. On the other hand, for the general case of having n greater than or equal to 2 states, the best we are able to furnish right now is basically k over 2 to the n. Okay, there's like a 2 to the n factor gap between this and k to the n, which is what we would like to get. But this is essentially our contribution, which is better for k greater than or equal to 6, right, compared to Ashutosh et al., but still not, there's still a gap between this and the currently known upper bound on f of nk. Yeah, so let me give you a taste of how we went about this to also tell you some of the challenges we encountered. So here is how you would probably go about constructing a lower bound. You got to do two things pretty much hand in hand. First, you propose a sequence of policies, call that sequence sigma, and then you try and create an MDP on which that sequence of policies will actually be a locally improving sequence. That doesn't work out, right? You come back and do something with sigma. You have to do both of these things, okay? So us being human beings, right, there's natural ways in which we might come up with a sequence of policies. So it is two states, okay? So our policies essentially are pairs, okay? We have to give one action for the first state, another action for the second state. I've just sort of compactly represented a sequence sigma as a matrix here, 5 by 5. So what this means is an entry here would correspond to a policy that takes action 0 at state 1, action 1 at state 2, and so on, right? So one sequence of policies, k-squared policies we might propose is you've got to finish up the first row, then go to the second row on the last column, then come back, right? Do it like a snake, right? Yet another, right? If you're in a different sort of creative mode, you might finish the first row and then go down the first column, come back, go up. Remember, we have to switch one row or one column at a time, okay? Not both at the same time, because they have to be neighboring policies. Okay, and then after you do all this, life comes at you, okay? So you realize that, in fact, neither of these, okay, neither sigma 1 nor sigma 2 can possibly be a locally improving policy sequence on any MDP, okay? This is actually not very hard to see, but I'll give you the intuition for it. So here's a picture that you can draw. Here's what's happening here. Each point I have drawn here, is this still shining? Okay, never mind. Like ij, for example, is a policy, okay, which is taking action I at state 1, j at state 2. The x coordinate of ij is the value of this policy at state 1. The y coordinate is the value at state 2. Okay, so I mean, if you have value functions over two states, it's going to look like this. Now the point is, it doesn't matter what MDP this has come up with. It has to satisfy these constraints. Okay. Any policy that takes action I on state 1 has to lie on a line. Okay, this is just an outcome of them having to satisfy the Bellman equations. So you see ij prime, and ij double prime all having to lie on this line. Similarly, there are lines on which the other actions, policies have to lie. There's similarly actions for the lines for actions at state 2. Okay, and moreover, there's things like the blue lines will all have slopes greater than 1. The other lines will all have slopes less than 1. Now think about it. Suppose we are trying to propose this as a policy sequence, okay? This 1, 2, 3, 4, 5 that I've shown here. Couple of things have to happen. Notice that because it is an improving sequence, you always have to be going to your right and going up, all right? It has next one has to dominate the previous one. In fact, we managed to do it over here, but you'll agree with me that the fact that we started on line I, switched out of it to line I prime, and then went back to line I. Now this is possible only because line I prime has a larger slope than line I. Okay, if line I prime had a smaller slope than line I, you couldn't really come back and also have monotonicity. Okay, so this is a constraint that any sequence of policies that you propose, right, has to satisfy. There is a symmetric thing for going from one j line to the other j line and so on. See, but if you have to do k-squared policies, you're going to have to switch many of these many times, okay? And so it turns out that the sigma 1 and sigma 2 that we proposed the sequences on the previous slide, they will violate one or the other of these constraints, okay? Which is the reason that they do not work. But all hope is not lost, at least for two-state MDPs. Here is actually a sequence that is implementable, okay? This particular one, you finish one complete row and then do the corresponding column, but so you go left to right, top to bottom, and again left to right, top to bottom, left, right, top to bottom. I mean, you can permute this and call it something else, but basically this is up to permutation different from what you saw in sigma 1 and sigma 2. And this can be implemented on a certain MDP, okay? So we have a procedure for generating this. In fact, it's like a full family of MDPs, but there is an MDP on which this will happen, okay? This will visit all k-squared policies. So that was a special case of having two states. What about the general case of having more than two states? Okay, in this case, the way we proceed is by partitioning the set of our actions into two sets. Okay, we have even numbered actions and odd numbered actions. And the way we construct our sequence is recursive. If you have the sequence for n minus 1 states, remember this is over k actions, that sort of gives us a way of getting the sequence for n states. But what is the idea? The idea is that we are going to get this sequence to visit every n-length string comprised of only the even actions. Okay, and we're going to use the odd actions to sort of bridge between gaps in this sequence of strings. I'll show you this with an example. So here is how our sequence looks for having 3 states and 6 actions. Okay, so you start at 0, 0, 0, go to 0, 0, 2, 0, 0, 4. Well, you'd like to go to 0, 2, 0 next, which is like the next increment of the counter with only the even elements, but you can't, right? Because 0, 0, 4 is not a neighbor of 0, 2, 0. So you use these odd numbered actions, 1 and 2, 1 over here, right, to go here. And then do the second column, third column, whatever. Okay, so here's, I think this is 52 policies for n equal to 3 and k equal to 6. In general, it's k divided by 2 raised to the n. It's more than that, okay? That's like a lower bound. What is the MDP on which that sequence is realized? It looks like this. Okay, again, there's, I mean, I've shown you only sort of 2 links going out from each state. Blue is a link that will be followed by all the odd actions. Black is one by all the even actions. They'll have different rewards, okay? The rewards themselves are specified by the formula over here. I mean, so I'm not going to like trouble you with the details now. But one interesting thing comes out of this, right? So you notice that the reward function here varies as something times k to the s, where s is the index of the state, right? So what this means is that the rewards essentially grow exponentially with the size of the state space, or the number of bits in the reward grows linearly in the size of the state space. It's a very uncommon MDP that's going to have this behavior. I mean, these are not the kind of MDPs we normally deal with when we are solving practical problems. So natural sort of insight by looking at something like this is, can we do this lower bound somehow without having this exponential growth in the number of bits, right, in the reward function? So the 94 example that I showed you was one where the reward functions would be constant size, but the transition function would actually have like an exponential number of bits. So we've not been able to do the lower bound, but this is the kind of thing that then motivates you to ask, can we show an upper bound if the number of bits is not growing like this? It's a constant. And that's what you saw in Dibyangshu's work, right, where he used the fact and the assumption of having a constant number of bits in rewards to upper bound the number of steps Howard's policy iteration would take. Okay, so you don't have to take my word for the correctness of this. We've written it out in the paper. There's also code to simulate the sequence and the MDP and so on. I'll leave you with this thought for future work. It is really the question of stochasticity. Okay, so the k-squared bound that I showed you for 2 states came from an MDP that had stochastic transitions. Independently, we have also shown, I didn't tell you this, but it's there in the paper. If you are limiting yourself to MDPs with only deterministic transitions, and you have 2-state MDPs, you actually have an upper bound of something like k square over 2, okay, on the number of switches that you can make, the length of your sequence, which essentially summarizes to meaning that if you have only 2 states, it is necessary, okay, to have stochasticity to realize a full-length, locally improving policy sequence. In subsequent works, yet other students of mine have shown this idea also extends to having n state MDPs. So if you have an n-state MDP restricted to have only deterministic transitions, the length of the LIPS is at most k minus something to the n. Okay, you cannot really reach k to the n with a deterministic MDP. That is like the sum and substance of this thing. So if we have to go to k to the n as a lower bound, you could only do that if you can using stochasticity, certainly not without stochasticity. So a current bound of k over 2 to the n comes from a deterministic MDP, okay, not from a stochastic MDP. So possibly one direction to think about if you want to like do better than that is to think about bringing in stochasticity in some meaningful way. Good place to start would be to look at the smallest problem instance we haven't solved yet on an MDP with 3 states and 3 actions, okay, which has 27 policies. Can you show, right, that there is a sequence of 27 policies which are improving, or show that such a sequence does not exist, okay? So I'll thank you with that.
So we have time for one quick question.
So one quick question. If I understood right, then you start from the policy, and every time you take a step, you improve.
Yes.
And when you say it is Hamiltonian, basically no matter where you start, you can improve to the best policy.
No, on any MDP, no matter where you start,
When you have an Hamiltonian, like exactly like
there is a particular way of improving.
exactly, so you can
Yeah.
go to the same. But
Yeah.
so in deterministic, you say that it is not. Then it means that there are some places you can start that you can not reach the max.
You will reach the max, but you will not visit yet other policies. Every policy will visit the top.
But can you visit the top from every place?
Yes. Yep. Done?
Okay. Yeah. So okay. So thanks the speaker again.